today I'm going to be talking about some of the more machine learning side of the work that I've been doing, and it's actually inspired by a lot of the problems and challenges that we have when actually trying to bring machine learning techniques to the real world. So I'd like to start with a little bit of a test, and I haven't done this remote before, so we'll see how this goes. In particular, I want to give you a little machine learning problem, and your training data set is on the left. The three paintings on the left were painted by Brock, and the three on the right in the middle were painted by Cezanne. And your goal is to learn from these 6 training points on the left in order to classify the data point on the right. So can you enter in chat which of the 2 paintings, what artist you think painted the picture on the right? So we have one Cezanne and one Braque so far. Cool. So we have a few. The more popular one seems to be Brock, which is the correct answer. And you can kind of notice this by looking at the style of the painting, seen in the training data points, and also seen in the test example, and all the kind of straight and more pronounced lines. And so it seems like you all are pretty good learners, and in particular, you're able to learn from a very small amount of data. And this is something that is very challenging for computers to do, for example. You're only given 6 data points, and you're able to learn from those 6 data points how to classify a new example. And the reason why you're able to accomplish this is the fact that you weren't starting from scratch. Oftentimes when we train machine learning systems, we kind of initialize their weights randomly and train them for the task. And if you were to do that in this case, it would be completely hopeless to be able to learn from only 6 examples. And so the way that you were able to do it is through previous experience. You probably haven't seen these particular paintings before. You may not have even seen paintings from these particular painters before, but you have experience looking at textures. You kind of understand, and you have previous experience about seeing different paintings and seeing the different styles of different painters. And you can use this to be able to make a prediction from a small amount of data by combining your previous experience with this tiny little training data set. So now I'd like to get to the question of, well, how would you actually get a machine to accomplish this? So we know that training, kind of our typical machine learning paradigm of training from scratch, would do very poorly here. And so depending on what area you're in, you might think a little bit differently about how to solve this few-shot learning problem. You might try to model the image formation process, or leverage somehow the geometry of the image. You might try to kind of use SIF features or hog features with an SVM, where the SIF features are encoding information about what you think is kind of in the image, or you might try to fine-tune from ImageNet features, or do some sort of domain adaptation from other painters. Now, one thing you might notice with kind of all these different kinds of approaches that you might use to solve this problem is all of them are injecting some sort of structure, or some sort of domain knowledge or prior knowledge into your machine learning system. And the other thing that you might notice is as you move down from top to bottom, we're kind of moving from having a lot of human priors and a lot of human domain knowledge to more data-driven priors. And arguably the systems on the bottom have been more successful than the systems on the top. So with that in mind, one of the questions I'd like to talk about today is, can we kind of take this to the extreme? And instead of trying to transfer knowledge from previous experience in an ad hoc way, can we try to explicitly learn priors from previous experience that lead to efficient downstream learning? Can we learn how to learn? And this is what's referred to as meta-learning. Can we kind of take our previous experience, learn priors from that previous experience in a way that allows us to quickly learn new tasks? So an outline of what I'll be talking about today. First, I'm going to give an overview briefly of meta-learning, and in particular, meta-learning to solve the kind of problem that I showed at the beginning of the talk. And then I'll talk about a really peculiar problem that comes up with meta-learning algorithms and how we might solve that problem. And lastly, I'll talk about how we can think about scaling meta-learning to very broad task distributions towards maybe even being able to solve the task that I gave you earlier. Okay, so let's first get into how meta-learning actually works. And we'll look at an example to do this. So one very popular example in meta-learning is actually the few-shot image classification problem, similar to the one that I showed you before. And in this case, we'll look at a classification problem based on images from the ImageNet dataset. So in this case, your training dataset is going to have 5 different examples, one example for 5 different classes. And your goal is, given these 5 examples in your training dataset, can you classify new examples as being among one of those 5 image classes? And this will be the test examples for this task. Now, how might we actually go about solving this? Well, in particular, you could think about the case of when you might have image data from other image classes. How can you set up that data from other image classes in a way that would prepare your algorithm for solving this problem laid out here? And in particular, what we can do is we can, this is what we want to be able to accomplish at test time, we can structure image data from other image classes into mini training sets and test sets, do this for many different image classes, and train our algorithm such that after it sees the training data on the left, it can generalize to examples on the right. Doing this for many different tasks across many different training classes, learning how to learn each of these classifiers, such that when we're presented with new classes at meta test time, we can effectively make predictions from small amounts of data. So this is how meta-learning works in a nutshell. And these different tasks, they could correspond to image classification tasks, but they could also correspond to other tasks like reinforcement learning tasks or regression tasks or something else. So we want to leverage the structure of tasks in the meta training dataset in a way that allows us to learn a new task with a small amount of data for a new test task, for example. Okay, so how do meta-learning algorithms actually solve this problem? There's a few different ways that you could think about doing this. One very popular approach is to take the tasks in your meta training set, parameterize your learner, the thing that's going to be learning from each of these training sets using a neural network. What you can do is you can take this training data, which is labeled, pass this into a neural network, and then also pass in new test examples to this neural network and train this neural network with supervised learning to output the correct label. And do this for all of the tasks in your meta training data set such that it can do this even for new training sets. So this is one very simple approach where the neural network is essentially handling every part of the learning process. And you can write this out in a general form of some function, f, and the neural network that takes as input a training data set dtrain, a test example xtest, and predicts the label corresponding to your unlabeled test data point. So this is kind of the general form of what a meta-learner often looks like. Now, another way we can kind of approach the meta-learning problem that's also been fairly popular is to embed an optimization process inside your meta-learner, and then learn different elements of that optimization process, such as the initialization, the learning rate, and so forth. So you could take some neural network, some initialized neural network, take your training data set, run some optimization on that neural network and that training data set to produce another neural network, and in that neural network should be able to take in test examples and produce the correct label. And then you can backpropagate through this entire process to the initialization, to the learning rate, and so forth to train this optimization process to be good at few-shot learning, at learning from small data sets. And this is the key idea behind the model-agnostic meta-learning algorithm, or MAML, and a range of other algorithms. Okay, and it's worth mentioning that this form, even though it has this gradient operator, this optimization process inside, this optimization process, at least for things like gradient descent, is differentiable. So you could essentially view this as the same computation graph as before, that's taking in a training data set and a test data point and predicting a label, where you're going to be optimizing over the kind of free parameters of this optimization process, such as the initialization. Okay, so those are kind of two approaches to meta-learning. And I'll give a couple examples of what meta-learning can actually accomplish. So you could combine meta-learning with reinforcement learning, like I mentioned before, such that if you train a meta-learner to be able to adapt to running in different directions, after running model-agnostic meta-learning, you can adapt a policy to the task of running forward after just a single gradient step, for example. And you can also adapt it to the task of running backward, again, with only a single gradient step needed and a small number of trajectories. So that's one thing that you can do with meta-learning. One other thing that you can do with meta-learning is apply it to imitation learning. And this is quite nice because imitation learning typically requires on the order of hundreds of demonstrations, which are typically pretty expensive to collect. And what we can do is we can train a meta-learner across many different objects such that when it sees a single demonstration that's provided via teleoperation at test time that looks like something like this, the demonstration shows that the robot placing the apple into the bowl. And then from this single demonstration, it's able to adapt its policy to these to the task. It looks like there's a bit of lag in the video, but it's able to perform this task for different initial positions of the object, even though it's never seen these objects before. And you'll just have to trust me that it's able to accomplish the task here. Okay, so we can combine meta-learning with imitation learning and reinforcement learning to be able to very quickly adapt to new objects, to new reward functions, and so forth. And it's also worth mentioning that there's a Bayesian perspective on meta-learning as well, where you can view meta-learning as approximately learning priors in this hierarchical Bayesian model, the prior P of phi given theta, such that when you integrate your prior with kind of the evidence from a small amount of data, you can acquire a posterior over your task-specific parameters phi. Okay, so that was a very brief overview of meta-learning, enough to allow us to dig into some of the details and some of the challenges of this problem. Okay, so one of the things I'd like to talk about is how we actually go about constructing tasks for meta-learning. So before we talked about how we could set up tasks by constructing a training data set and a test data point for each of your tasks. And those could look like something like this, where your training data set contains different images and the test data point contains images from those classes and so forth. So it looks something like this. And one of the things that's worth noting here is typically when we construct these tasks, we randomly assign a label to each image. So in the first task, the label for mushroom is 1, and in the last task, the label for mushroom is 0. So we randomly assign class labels to image classes for each task. We also randomly sample image classes, like 5 image classes to be used in each task. And one property that results from this procedure is that the tasks are mutually exclusive. And what I mean by that is there doesn't exist a function that could solve all of the tasks. For example, there isn't a neural network that could solve both task 1 and task 3 at the same time because they're inherently mutually exclusive, they're incompatible with one another because the same image classes have different labels. So this is maybe kind of interesting. And one, again, resulting fact from this is that because they're mutually exclusive, because you can't learn a single neural network that performs all these tasks, the meta-learning algorithm must use the training data on the left in order to infer the label ordering. And otherwise, they won't be able to solve all of the tasks in the meta-training set. So this follows directly from the fact that the tasks are mutually exclusive. Okay, so now what I'd like to ask is, what if the label order is consistent across tasks? What if, for example, mushrooms always have labels 1, dogs always, these white dogs always have label 2, birds always have label 0, and so forth? In this case, This seems like a fairly innocuous change to the way that we're setting things up. We still have all these meta-training tasks. They all have different image classes and so forth. But now the tasks are mutually exclusive, meaning that a single function can solve all the tasks, a single neural network. And what this means is that the MetaLearner doesn't actually have to use the training data in order to solve the task. It can just simply learn to classify inputs irrespective of detrain. And while this change seems fairly innocuous, this can actually significantly deter the performance of meta-learning algorithms. So if, for example, we pass this into a neural network meta-learner and train it in using the data that I showed on the previous slide, then what it could do is just completely ignore this training data set that's being passed as input and only classify the examples that are passed in. And the same thing is true for an optimization-based meta-learner. It can essentially construct its initialization in a way that the gradient update doesn't actually have any impact on the functionality of the neural network. And as a result, it ignores the training data and only classifies examples using kind of this fixed functional neural network. And so this is a problem because if we, for example, then give it new image classes, like the ones shown on the bottom, it doesn't know how to adapt to different image classes. It doesn't know how to adapt to, doesn't know how to solve this task, because it would have to solve this task, it would have to understand the label ordering in this case, what the label for golden retriever is, what the label for lion is, and so forth. And so if you train a MetaLearner on this data and then test it on something like the examples on the bottom, then the performance plummets. It goes down to around 7.8% accuracy on 20-way one-shot tasks and around 50% accuracy on 20-way five-shot tasks. So this is pretty terrible. This is actually on the Omniglot dataset, and typically algorithms, when trained on mutually exclusive datasets on Omniglot, get performance in the high 90%. Okay, so this is potentially pretty disturbing because it seems like we'd made a fairly innocuous change to the training setup, and the performance is drastically lower than what it was before. Is this a problem? Well, one thing you might say is, well, okay, if we just want to solve image classification problems, like we can just shuffle the labels. We know how to do this, and we're fine. We can just go back to the setting where we can shuffle the labels, and then we'll get our performance back of 95% or so, or something like that. Or this also isn't a problem because maybe we're always going to see the same image classes as what we saw during training, and then we don't need to adapt at meta test time. So maybe everything is all fine. But there are some examples that I'll show in a second that it is very hard to shuffle the labels, quote unquote, to actually construct tasks that are non-mutually exclusive, and for which we need to be able to adapt with data for new tasks. Okay, so what do those examples look like? So one example, inspired by settings in robotics and reinforcement learning, is if we want a robot to learn different tasks like closing a drawer or using a hammer to hammer a nail or stacking objects. If we do meta training across these tasks, if we don't tell it what the task is, like if we don't tell it that it should be closing the drawer, it needs to completely figure that out from scratch in a way that's fairly blind, then this problem won't necessarily exist. But if we tell it to close the drawer, we tell it to use the hammer or stack it, or even give it an image of the environment, there exists a single function that can solve all of these tasks given those inputs. And such that if you give it kind of those indications of what the task is, if you then want the robot to solve a new task through trial and error with a small amount of trial and error, it'll learn how to, it'll simply ignore the trial and error at meta training time in a way that will prohibit it from actually being able to understand a small amount of trial and error for the test task. So this is one setting where this is a big problem. We won't actually, if it learns to ignore trial and error data for all the meta training tasks, then it won't be able to learn the test task through trial and error, through fast trial and error either. Yeah, so essentially, if you tell the robot the task goal, or if you give it an image of the task, the robot can simply ignore the trials. Another example is something like pose prediction. So say you want to predict the pose of some object like a couch or a TV, and you give it training data for each task, and you want to be able to make predictions for new poses, new orientations of that object. In this case, if it just looks at the image, it can see what the object looks like, and it can just learn how to predict the pose of all of the training objects, irrespective of the data shown on the left. So it can just ignore all the data shown on the left, learn the model that predicts the orientation of all the training objects, such that when it then sees a new object, if it doesn't know how to actually adapt from the data, it won't be able to perform well. But if it does if it does figure out how to adapt to the training data, it will be able to actually adapt to this new test task. Okay, so essentially the model can memorize the canonical orientations of all the training objects in a way that doesn't allow it to be able to adapt to new test objects. Okay, so can we do something about this? It seems like it's a problem. And this is what we look into next. So if the tasks are mutually exclusive, we know that a single function cannot solve all the tasks, for example, due to label shuffling and hiding information. In this case, we're fine. But if the tasks are non-mutually exclusive, a single function can solve all of the tasks. In this case, there's actually multiple solutions to the meta-learning problem. There's one solution, and we can take our kind of existing form of a meta-learner here, where we take in as input a training data set and a test input. One solution is to essentially memorize the canonical pose from the pose prediction example in theta and ignore detrain when making predictions about examples. So this is one solution that would give us perfect prediction accuracy on the meta training set. And another solution would be to carry no information about the canonical pose in your meta parameters and instead acquire that information from your training data set. This is the solution that would actually adapt to your training data set. So these are these two solutions, and the solution that we prefer is the latter one, and this is the one that actually adapts to the training data set. However, both these solutions can perform very well in the meta training data set. And there isn't just these two solutions, there's an entire spectrum of solutions based on how much information about the canonical pose you're storing in theta, and all of these solutions perform very well in the meta training set. And these solutions are essentially about how information flows. If information is flowing from theta or if information is flowing from detrain when making predictions about the label for X test. And this kind of realization also suggests a potential solution, which is to control how the information flows. We can encourage it to carry more information from detrain in comparison to from theta as a potential solution. So this is pretty cool. And in particular, what we aim to do here is what we call Meadow Regularization, to try to prevent this kind of form of overfitting to the meta training tasks. One option here would be to maximize the mutual information between the model's prediction and the training data set for a task, given your test input. And this is something that would encourage it to leverage information from detrain rather than from theta. We found that this was pretty difficult to optimize in a tractable way, and so what we choose to do instead is to minimize the meta training loss, but also minimize the amount of information in theta as a regularizer. And what this does is that this says that if you want to do well on the meta training loss, then you need to use information, you need to kind of leverage information from detrain, because if you're going to be minimizing information in theta, then you're going to need to get that information, get back some of that information from somewhere. And if there's information available in detrain, you should leverage that information in detrain instead of like putting it into theta and leveraging that information in theta. And so in particular, what this will look like is we have our meta training loss, that's some loss on our meta parameters and our meta training set. And we're going to add this term here, which is minimizing the KL divergence between the we're going to place a distribution on our parameters theta, minimizing the KL divergence between that distribution and some prior distribution. This is essentially a kind of a Bayesian neural network and corresponds to Bayesian regularization on the parameters of our neural network. Although in this case, we're going to use this beta term to control how much regularization we have relative to the meta training loss. Okay. And so what this does is this places precedence on using information from detrain over storing information in theta, and this will encourage it to actually adapt to detrain and encourage it more towards the solution in turquoise compared to the solution in pink. And then you can combine this with your favorite meta-learning algorithm. It draws a lot of similarities with kind of a standard Bayesian regularization over specifically the meta parameters. Okay, so how does this actually work in practice? We constructed a version of Omniglot where we didn't perform any label shuffling, and the labels were always consistent for different examples. We're calling this non-mutually exclusive Omniglot. We can see the results that I showed before, where mammal performs very poorly. We also compared to an approach called task-agnostic meta-learning that tries to, that kind of places a different form of regularization on the parameters, and we find that this also performs very poorly and isn't effective at preventing the kind of the form of overfitting that I mentioned before, where it ignores the task training data set. And what we find is when we combine this meta-regularization by placing a distribution on the parameters, we get significantly better performance, and we come closer to approaching the performance of mammal on the mutually exclusive version of Omniglot. Okay, and then there's also the post-prediction task that I mentioned before. In this case, where you don't want to memorize the canonical pose information. And in this case, we find that mammal and conditional neural processes, which is more like the first type of meta-learning that I mentioned, both perform very poorly with a mean squared error of 5 and 8 respectively. Whereas if you apply meta-regularization on both these two algorithms, it significantly improves their performance and lowers their mean squared error. Lastly, one thing I'd like to emphasize here is that while Bayesian regularization is kind of, while this form of meta-regularization is very similar to meta-regularization used in standard supervised learning, where you place that regularization is very important. And for example, for conditional neural processes, if we use this Bayes by backprop or BBB approach on all of the parameters of the neural network, including those that are used for adaptation, then you still perform pretty poorly, getting a mean squared error of 7.73. Also, kind of simple weight decay approaches don't seem effective either for solving this problem. Whereas specifically placing the meta-regularization on the meta parameters is where we get the best performance here. Okay, great. One last question that I think is worth answering here is, does meta-regularization actually lead to better generalization from a theoretical point of view? And what we did here is we defined P of theta to be kind of an arbitrary distribution over theta that doesn't depend on the meta-training data. This will be our prior over theta. And for example, this could be like a 0-1 Gaussian distribution, a standard normal distribution. Then we can show that for mammal, with a probability of at least 1 minus delta, we get a generalization bound that looks like this. And in particular, this equation is maybe looks a bit like a lot, but what this corresponds to is measuring the generalization error as being bounded by the error on the meta-training data set plus a meta-regularization term. And this indicates that if we can successfully optimize the meta-regularized objective, this corresponds to actually a bound on our generalization error. And you can actually show that with a Taylor expansion of the right-hand side and a particular value of beta, you can directly recover the meta-regularized mammal objective. And the proof for this draws heavily on some previous work that was looking at pack-based bounds for transfer learning and so forth. Okay, great. So some intermediate takeaways from this part of the talk is we talked about a form of meta-overfitting that we referred to as memorization. And what this corresponds to is memorizing the training functions, Fi, corresponding to the tasks in the meta-training dataset. Memorizing the function that can solve all of the training tasks, irrespective of the dataset that you could use to adapt to. In many ways, this draws analogs to standard overfitting, where you memorize training data points in your training data set. the kind of analogy here is that the form of overfitting in meta learning essentially lifts the form of overfitting from data points to tasks or data sets in your meta training data set. And this is somewhat natural because meta learning in many ways is lifting standard supervised learning into a higher, kind of treating data points and tasks as individual data points and optimizing over those tasks, whereas in standard learning, you're optimizing over your data points. And we also talked about a form of meta regularization that tries to combat this form of overfitting, this form of meta overfitting, by controlling the information flow. And this also can be viewed, and while this doesn't kind of directly correspond to forms of standard regularization where you're regularizing the hypothesis class, there is an interpretation of meta learning as essentially regularizing the description length of your meta parameters, and this does draw an analog to the kind of regularization that we see in standard supervised learning. Although I guess it's also worth noting that for neural networks, regularizing your hypothesis class isn't always a very effective form of regularization, and we often don't actually use Bayesian neural networks to regularize deep neural networks. And so it's kind of interesting that in this case seemed to be particularly beneficial and useful in this meta learning problem in comparison to how well it works with deep neural networks. Okay, before I move on to the next part, are there any questions? Okay, so let's move on. One natural question to go from here is it seems like we've made meta learning a little bit less susceptible to the task distribution that we train it on, such that we can train on non-mutually exclusive task sets. Now, can we think about scaling meta learning to very broad task distributions? And well, why is this important? So we could think about whether meta learning has actually accomplished our goal of making adaptation fast, such that we can learn from small data sets like the 6 data points that I showed to you at the beginning of the talk. And I would say that the answer to this is only sort of. We've had some success. We've shown that we can adapt to new objects, such as predicting the orientation of new objects or imitating a trajectory for new objects that you haven't seen before. We can also adapt to new goal velocities, like I showed with the quadruped here. We could also adapt to new object categories, such as the classification example. But in all of these cases, the test task is in many ways very similar to the tasks that you're seeing during meta training. And so one natural question to ask is really to demand more of our meta learning algorithms and ask if our meta learning algorithms can enable us to adapt to entirely new tasks or data sets, such as the data set that I showed you at the beginning of the talk. And of course, if we want to adapt to things that are very different from some of the tasks that we saw during meta training time, we need to still obey the kind of one of the central principles of machine learning and also for meta learning, which is that the task distribution that we train on should be the same as the task distribution that we test on. And if we want our meta training task distribution and our meta testing task distribution to be the same, and we want to adapt to entirely new tasks, this means that we need a very broad distribution of tasks for meta training, such that this is still such that the entirely new task that we want to adapt to at meta test time is still within the support of the tasks that we see during meta training. So where do we get that broad distribution of tasks? There are a few different ideas and approaches that we've been thinking about for solving this problem. One idea is to kind of have the algorithm construct tasks itself instead of having the practitioner do that. But what I want to talk about today is if there are kind of existing benchmarks or existing things that we can look to for this distribution of tasks. And in particular, I want to see if we can look to reinforcement learning benchmarks, because reinforcement learning is a very natural way to think about meta learning, where we want a robot to be able to solve a new task, for example, given experience doing many other motor control tasks. And maybe we can look to reinforcement learning benchmarks. So there have been a number of reinforcement learning benchmarks ranging from the OpenAI Gym to the Atari learning environment to this paper that was looking at proposing benchmarks for robotics tasks. And while these have been, of course, tremendously valuable to the reinforcement learning community, it isn't clear if they're particularly suitable to studying meta learning. And in particular, in something like OpenAI Gym or the Surreal benchmark, The number of tasks is relatively small, maybe kind of in the handful of task range, so kind of single digits still. And they're also kind of varying variability between them. So in OpenAI Gym, the tasks are completely different from each other with different degrees of freedom and so forth, and it's unclear if you would be able to transfer between them. And they're kind of a very small number of tasks. And for this real benchmark, they're a little bit more similar in that it's kind of the same robot in a similar environment, but there's only like 5 or 6 tasks. And then if we're only kind of training on 5 or 6 data points, essentially 5 or 6 tasks, being able to generalize to an entirely new task is in many ways hopeless. Now, what about the Atari learning environment? I think that this is in many ways more promising. There are many more games, and we could conceivably think about kind of training across all of those different games. But the kind of similarities between games are completely different. The background, the control scheme, what things look like, and what you're actually trying to accomplish are completely different in all of these different games. And so again, trying to transfer and really pick up on those commonalities between environments is very difficult. And we may not, even if we pick up on the commonalities between different environments, those commonalities may not actually allow us to transfer to new tasks with a small amount of data. Okay, so it seemed like there weren't a lot of tasks. There aren't a lot of like good benchmarks for solving this. There's a question that says, are there any thoughts on how broad the distribution of meta-training tasks needs to be before you get a certain kind of generalization? And I think this is a really good question. I think that in general, this kind of is fairly similar to the question in supervised learning of like how broad does our training distribution need to be in order to generalize to new test data points. I think that of course we need for things to work with our current algorithms, it needs to be within the support of the meta training task distribution. This is a very natural thing to ask for, although of course it's very difficult to say when we kind of have these non-parametric changes between tasks, when tasks aren't vary in a very like parametric way, then it's really hard to say what is in support and what's not in support. So I think that this question is good, and it's something that will, in many ways, at least in my opinion, we'll need to answer empirically for different task distributions that we see. Okay, so motivated by this, we actually said, okay, well, if we want a benchmark, maybe we should just create one ourselves. And the things that we wanted here was to have 50 or more qualitatively distinct tasks so that we can maybe hope to generalize to new tasks if we're training on a sufficiently large number of tasks. We want to have a shaped reward function and more sparse success metrics so that we could control the degree of difficulty of the reward function that we use, and so that we don't have to worry about kind of the exploration problem itself when trying to solve this. We also wanted all the tasks to be individually solvable to allow us to focus really on the multitask learning and the meta learning component of it, compared to just simply the reinforcement learning problem itself. And we also wanted to have a unified state and action space and environment to allow us to facilitate transfer and really such that there were some strong commonalities between the different tasks. And this is kind of in stark contrast to things like Atari, which have a completely different state space, completely different action space, and a completely different environment. So motivated by this, we construct this benchmark with 50 different tasks that all correspond to robotic manipulation tasks with an arm shown here. And in this case, we explicitly split it up into a training task of 45 tasks and a test set of 5 tasks so that we could really encourage the ability to transfer to entirely new, qualitatively distinct tasks. And we referred to this as the meta world benchmark to kind of emphasize that we hope people to try meta learning algorithms on this, although it's also been used for single task reinforcement learning as a benchmark as well, and for multitask reinforcement learning, as we'll see in a few slides. Okay, so how do algorithms actually work when we test them on this benchmark? And the result is that meta learning algorithms actually really seem to struggle. So we ran, we call the specific benchmark that I showed before ML45 because we're meta learning on 45 tasks and testing on 5 tasks. And what we found is that when we tried to transfer to the test task, the performance was very low, around the kind of 20 to 30%. And these are really 3 leading meta reinforcement learning algorithms. And so looking at this, you're like, okay, well, maybe we just need more meta training tasks. Maybe or maybe we need tasks that are closer to the tasks that are seen during meta testing because the transfer is very difficult. But it turns out that the meta training performance is also remarkably low, getting kind of performance less than 50% success on the tasks in the meta training data set. And so this was somewhat puzzling to us. Even on the meta training tasks, we were seeing very poor performance. We weren't even able to fit the tasks that we were given during training. And so this kind of encouraged us to look at, well, how do multitask reinforcement learning algorithms do just on the tasks that they're trained on? And in this case, we found that even kind of leading multitask reinforcement learning approaches weren't able to get performance that was very satisfactory to us, with success rates in the kind of 20 to 30% range or 35% range. So why the poor results? We came up with lots of different hypotheses, such as maybe there's an exploration challenge, but we specifically designed the tasks to be individually solvable, so it doesn't seem like that's a particular problem. Maybe it's a data scarcity problem, but in all the results I showed before, we gave them really plenty of samples to use in their budget. Maybe it's limited model capacity, but we kind of tried different neural network architectures, and we were giving them all really plenty of capacity. And so the final thing that we looked at is, well, okay, maybe it's an optimization challenge. And what we did is we compared multitask learning to just independently training policies on each of the tasks. And what we found is that training independent policies on the 50 tasks in the benchmark performs substantially better than just trying to run multitask SAC or soft actor critic on all of these tasks. And this is controlling for capacity, controlling for the total amount of data, and so forth. So this suggests to us that it's really a optimization challenge. So we wanted to get to the bottom of this because it seems like if we can solve this optimization challenge in multitask reinforcement learning, that will allow us to go back to the meta learning setting and also try to improve the results there. So we looked at prior literature on multitask learning. There's really two classes of literature, at least from what we found. One is looking at architectural solutions, so thinking about how you could change the neural network architecture in a way that is amenable to learning multiple tasks. And there's really all sorts of ideas in this body of work. But it seemed like all of these kinds of ideas were either specific to the particular domain that they were looking at, like a computer vision domain or a natural language domain, or they weren't really helping our performance. So we did look at multi-head architectures, and we looked at film on the left, and they helped to some degree, but they really weren't allowing us to bridge the gap between independent training. The second set of approaches that we found were approaches that tried to weight tasks dynamically throughout the course of training, where you want to essentially place a weight on the task that you're training. Maybe you're training on 3 different tasks, and so you learn a weight for each of those tasks. And you try to dynamically trade off these weights based on how each task is performing and what the gradients look like, for example. And in this case, we also found that these approaches weren't helping us, or weren't kind of improving performance on this benchmark. So it seemed like we needed a new approach here. And we had a few hypotheses about what was going on. Our first hypothesis is, well, it seems like maybe gradients for different tasks are often conflicting with one another, because if they weren't conflicting, then it seems like they should be able to learn reasonably. And in particular, if the gradients are kind of interfering with one another, we think that we would see a negative inner product of the gradients, essentially gradients that point in different directions. And our second hypothesis is that when they do conflict, they cause more damage than expected. So conflicting gradients in and of itself shouldn't be a problem. It should be that you can simply average those gradients to get a gradient direction that allows you to make progress on your objective. But our hypothesis is that due to some properties of the landscape, this conflict was causing more damage than what we were expecting. And so to see this, let's look at a really simple example. So say we're kind of have a 1D parameter theta and our loss function on the y-axis, and maybe our loss function looks like this, where we have positive curvature, which is fairly standard in loss functions. If we're at this point during the optimization procedure, and maybe for the gradient for one of our tasks looks like this, and the gradient for another task is different, then this is going to, maybe the gradient for the other task kind of wants us to go right, and it kind of feels strongly about going right in this space, and so it has a very large gradient pointing, very large negative gradient pointing to the right, pushing the theta to the right. So if that's the case, and if we actually go to the right, then for this task visualized here, according to the gradient, we would end up where this point is here. But in reality, because of the high curvature, we actually end up all the way up here. And so even though the gradient was telling us that kind of compromising this task for the other task was a good thing to do, in reality, because of the high curvature, it actually was a poor choice. And high curvature also means that for the other task, even though you had a large gradient pointing the other direction, maybe because you're on the left side of this curve, that actually you're going to be overestimating your improvement, and you'll actually also not go as far as what you expected. And this sort of situation will happen when you have high curvature and when you have a large difference in gradient magnitude, such that one gradient dominates the other one. Okay, so these were hypotheses for this problem, and our idea for fixing it was to try to avoid making other tasks worse when taking a gradient step. So when you take a gradient step, if another task would have to compromise its performance, try to avoid compromising, essentially, or try to avoid forcing other tasks to get significantly worse. And the algorithm for doing this is really, really simple. What we do is, if two gradients conflict, if two gradients have a negative inner product or a negative cosine similarity, then project the gradient onto the normal plane of the other gradient. So, for example, if the gradient for task I and the gradient for task j have a negative cosine similarity, then project the gradient for task I onto the normal plane of task j, and project the gradient of task j onto the normal plane of the gradient for task I. So the result is the green, the two dashed lines here, the result of that projection, and then you average the projected gradients when applying the update. And then if the two gradients don't conflict, then just leave them alone. Use those task gradients as normal. So this is it. This is the algorithm. Really, really simple. And we call this project conflicting gradients, because that's exactly what we're doing, or PCGrad for short. And what we found is that on the Meadow World benchmark, we saw really substantial gains in performance. So the purple curve is showing PCGrad. This is the performance as a function of the number of environment steps. And the yellow and red curves are showing what multitask learning does on these tasks. And we see a huge gap between the yellow and red curves and the purple curve. And further, we're able to significantly improve upon independent training, both in terms of efficiency and to some degree in terms of the performance after a certain number of environment steps. Although towards the end, with enough data, we see that they converge towards each other. Okay, so it seems like this worked pretty well. And we also look at read learning tasks. We also applied those to supervised learning tasks. And we found that something like independent training gives you something like 42% or 49%, whereas PCGrad is able to achieve 71% accuracy here. And we also took an architectural approach called routing networks, which is shown in the fourth row, that gets 74.7% accuracy. And we found that if we combine that architecture with PCGrad, applying PCGrad to all of the shared parameters, we're able to also significantly increase that accuracy from 74.7 to 77.5. Likewise, we also looked at another benchmark that we'd seen used in the literature, where you have 3 tasks predicting segmentation depth and surface normals. And here again, we found that we were able to consistently outperform previous approaches by combining PCGrad with another architecture, this time the architecture called MTAN. So the takeaways here is that PCGrad also helps with multitask supervised learning and is complementary to the different architectural solutions that I mentioned before. Okay, so now you might be wondering, well, why does this actually work? I gave some kind of hypothesis and some intuition for why this might be a good idea. but is there more that we can say here? So the first thing that we did here is we looked at, well, PC-Grad is really doing two things. When we project the gradient, we're changing both the magnitude of that task gradient as well as the direction of that task gradient. So we wanted to decompose the effect of changing the magnitude and changing the direction. So we did exactly that. Purple is showing PC-Grad, the full version of the PC-Grad algorithm. Red is showing if we only change the direction, and blue is just showing if we only change the magnitude of the gradient. And this shows that only changing the magnitude really doesn't help performance much at all. And changing the direction does seem to be really important, but only changing the direction doesn't allow us to get the full performance benefit of changing both the direction and the magnitude. So it seems like both components are important here, with the direction being particularly important, which is something that previous works typically don't do. And the second thing we wanted to look at is kind of the mechanisms underlying the performance. So if we go back to the hypotheses that we mentioned before, we talked about having gradients that were conflicting with one another. And when they do conflict, they cause more damage because of high curvature and a difference in gradient magnitude, with one gradient dominating another. And we can write this down into really three different conditions. The first condition is conflicting gradients. Second condition is large positive curvature. And the third condition is this difference in the gradient magnitude. And for the sake of not having to list all of those three things, we call this the Tragic Triad, these three conditions. So that we'll refer to those three conditions as the Tragic Triad from kind of moving forward. And we wanted to see, can we construct a toy example where all three of these things exist and we see a difference between PC-Grad and just standard optimization? And what we found here is that here's a multitask learning objective shown in 3D on the left, composed of two task objectives that look kind of like logistic curves. These are showing the kind of the heat map of the loss function, with darker red being lower. And what we see is if we run, so the optimum for this task is kind of near the top of kind of following the curve to kind of the top of the picture. And what we find is if we run Atom on this task, we get an optimization trajectory shown in black, where it starts in kind of the bottom center, moves towards the kind of bottom of this canyon, and then stops. It isn't able to figure out how to go all the way to the optimum in the top left. And the red and blue arrows are showing the gradients of the two tasks. And what we see is here, we see kind of exactly those three conditions. We see conflicting gradients because these gradients are pointing in different directions. We see large positive curvature because we're in this canyon. And we also see a big difference in gradient magnitude because the red gradient is much larger than the blue gradient. And if we apply PC-Grad to this problem, we see that it doesn't get stuck and is able to traverse all the way to the optimum of this two-task objective. So this provides a little bit of empirical evidence that PC-Grad is able to mitigate these three conditions, but it doesn't completely answer the question of why this works. So there are two more questions that come up. One is, well, okay, this is kind of a little toy example that illustrates the effect, but is PC-Grad really provably better under these three conditions? And another question is, are these conditions actually why we see improvements on large-scale problems? So this is really a toy problem. We don't know if these conditions are actually occurring in larger-scale problems. So in an effort to actually answer these two questions, we actually looked at the theoretical properties of PC-Grad, and the short answer to this question is yes. It is provably better under these three conditions if you have large enough gradient conflict, large enough curvature, and a large enough gradient magnitude difference. And we were able to show this for the setting where you have two tasks that you're trying to learn. The math gets a lot hairier if you have more than two tasks. The longer answer is a bit messier, but under we can really formalize the conditions under which we expect the gradient of PC-Grad to produce a lower loss than the gradient of simply averaging the original gradients or the multitask gradient. Okay, and now the second question is, do these three things actually come up in practice? Which would suggest that these conditions are why we see improvements on large-scale problems. To do this, we took two tasks from Meadow World and just trained on these two tasks such that we can actually evaluate some of the conditions in the theorem on the left. What this plot is showing is the two purple lines are the per task performance for PC-Grad, and the two yellow lines are the per task performance of just running multitask SAC. So we see PC Grad does significantly better when training on these two tasks. And what we find is that if we try to evaluate the conditions in which, the percentage of the times in which condition A and condition B in this theorem are actually holding in practice, it's generally quite high. So this is shown in the dashed line and the dotted line. It's around the kind of 80 to 90% until around 50 iterations, and then it starts to kind of drop off a little bit down to 50%. And this is where we see kind of PC Grad performance starts to level off a little bit. And then we also see that the cosine similarity, the percentage of the time that they're actually conflicting, is around 50%, which is fairly constant, which also helps us explain why PC Grad is doing better. And then the last condition relates more to curvature, and we also measure the curvature of the critic loss for these two tasks, and we found it to be a very large positive number, which also explains why, which also suggests that these three things, it suggests that large positive curvature is actually occurring in practice with these large-scale neural network multitask learning problems. Okay, so to summarize this part of the talk, I talked about how scaling to broad task distributions is actually quite hard and it can't be taken for granted. First, there's a lack of good benchmarks, and for this we proposed a new benchmark, the Meadow World benchmark, and we found that scaling is really primarily hindered by optimization challenges in multitask learning. And we also talked about how these three conditions of conflicting gradients, curvature, and gradient magnitude difference really seem to plague multitask learning and multitask reinforcement learning. And if we project conflicting gradients, this seems to be a pretty solid solution for solving this problem. Of course, any research really raises more questions. So some remaining questions is, does this PC Grad solution actually translate back into meta learning? And is this problem actually unique to multitask learning, or is it true for other problems as well? Okay, and so to summarize, I talked about kind of a kind of weird but ubiquitous problem in meta learning, as well as some optimization challenges when trying to scale up. If you're interested in learning more about some of these sorts of things, I actually taught a course on multitask learning and meta learning last fall, and all the lecture videos are available online. If you're working on meta reinforcement learning or multitask reinforcement learning, I encourage you to try out the Meadow World benchmark. And I'd like to thank my students and collaborators. Thank you, everyone. Any more questions? Okay, Sanjeev was asking, can you explain PC Grad briefly again, how general it is? How general is it? So I'll try to do this in 48 seconds. It seems like it might kick us off. So the way that it works is you simply take the gradients for each of the tasks that you have and project the gradient for a task onto the normal plane of the other task and vice versa. This is what you do if you have two tasks, and then you average the kind of resulting task gradients. If you have multiple tasks, then we iteratively project onto the other tasks for the conflicting gradients. And really it's quite general. It's really general to any gradient-based optimization where you have multiple tasks or where the loss composes into these different additive terms. So there's a question about if the projectome will make the magnitude too small. It does decrease the magnitude of the gradient, but we found that I guess empirically we found that it didn't make it too small. If you have more, like the more and more tasks you have, the more projecting you might be doing, which might make it smaller and smaller, but in practice we didn't find this to be too much of an issue. So Sanjeev's asking, is that a bit like doing the SVD of K gradients? I'm not sure. We haven't looked into that question in particular. Yeah, I'm not sure off the top of my head. Jeff is asking, have you explored other variants of PC-grad that use some measure of conflict other than cosine similarity? So in this case, I guess, I don't have any ideas of other metrics other than cosine similarity, in that I guess we're also using the, equivalently, we're using the inner product, in the sense that if the inner product is negative, then we perform this operation. I'm not sure of other measures that people have used to measure conflict. I guess you could also look at the magnitude. If the magnitude is very different, then you could also try to adjust for that as well. I think that implicitly, PC-grad is already doing that, because gradients that are larger but are more conflicting will have a larger difference in magnitude when you project, compared to gradients that are kind of smaller and less conflicting. And then Sanjeev is saying low dimensional approximation of space spanned by the gradients. I'm not quite sure exactly what you're asking. Okay, yeah, we can discuss later. There's one more question. Could the metadata sets have the same output space? So in the examples that I was showing before, we always assume that the kind of the thing that the labels is generally kind of the same output space. Like you're always predicting the orientation of the object, for example. You could also have different output spaces for different tasks, as long as there's kind of the output spaces that you're seeing at meta test time fall within the kind of range of output spaces that you have over meta training, and that your architecture can actually span those spaces. Okay, if there aren't any other questions, thank you everyone for showing up.
Thank you very much.